applications of linear relations, and adding details to distance-time graph stories. If we consider the example as shown on the graph below, it's talking about Faraz, who returned from jogging at noon and went to the fridge. He took out a bottle of water and began to drink the water. The graph represents the volume of water in the bottle over time, and it wants us to write a story about the volume in the bottle, the volume of water in the bottle, with as much detail as possible. So we can get our highlighter out and highlight the important information. So we're writing a story about the volume of water in the bottle. We want to include math terminology. But the key is we're writing a story. So we need to think about what the initial value and the final values tell us. Okay? Tells us, if we can look at the vertical scale, every box is 50 milliliters. So it tells us right here that we start with 350 milliliters of water in the bottle, and we end with no water in the bottle after 30 seconds. What does each section of the graph tell us? If we look at section A, the volume is decreasing at a constant speed because it's linear over 5 seconds. Okay, section B, the volume of water in the bottle is not decreasing. It's not changing, in fact, so he's not drinking at this point in time. And in part C, it's not as steep a line, so he's not drinking as quickly, but he is still drinking because the volume is decreasing. Can I get more information than that? Absolutely, because I know that the rate of change of volume with respect to time is just another form of slope. So that's what I need to do, is figure out the slope of each segment with respect of, figure out the slope, so the volume with respect to time for each segment, and I can give more detail. So if I think about segment A, if I go down from the beginning of the segment and right to the end, I can say my rise, it went down 150, so that's negative. Sorry guys, I don't have the Mobi, I'm trying to work with a mouse. And the run increased by 5 seconds, so that's positive because it got bigger. Now, we have to remember that rate of change is rise over run, and the rise in this case was negative 150 over the run, which is 5 seconds, and when we divide that, we get negative 30 milliliters per second. So the rate of change of volume with respect to time in segment A is negative 30 milliliters per second. It was negative, it tells us it's decreasing, and the 30 milliliters per second tells us the speed at which it's doing it. In part B, if I look, I start here, I end here. My rise is 0, my run was 15. When I substitute that into my rise over run equation, I end up with a rate of change of 0 milliliters per second. So the rate of change of volume with respect to time in segment B is 0 milliliters per second. The volume's not changing because the rate of change is 0. Segment C, if I look at this one, I'm going down. Again, sorry guys, I can't draw straight with the mouse especially. I went down 200 milliliters and over 10 seconds. So the rise is negative 200 and the run is positive 10. Again, rise over run, negative 200 milliliters over 10 seconds, which gives me a rate of change of negative 20 milliliters per second. The rate of change of volume with respect to time is negative 20 milliliters. And again, the negative is also telling us it is decreasing. Okay? If we want to write our story, we need to talk about Faraz returns from his jog at noon. He went straight to the fridge and got a bottle of water. And that's where they left off. The important part was he opened the bottle of water and drank at a constant rate. We can add the constant rate information to the story because it's linear. And now we can add the rate. It was negative 30 milliliters per second, and we can tell them how long he did it because he did it over 5 seconds. He ran out of air drinking and had to catch his breath. And if we go back to our graph, our run on that segment was 15 seconds, so we will say he did that for 15 seconds. And then he drank, and we can use the word slower and say it was at a slower constant rate because it wasn't as steep as segment A, but it was still linear, so it's still a constant rate. And it was for 10 seconds, because if we go back, the run over that whole segment was 10 seconds. Okay, before class, please do page 10, number 1. Have a good night, guys.